Linear systems are three equations in three variables. The primary tool we will use to solve these systems is called Gaussian elimination, named after the German mathematician Carl Friedrich Gauss. If the system has a solution, it is an ordered triple XYZ. A system in upper triangular form looks like the following: AX plus BY plus CZ equals D, Fy plus Ez equals G, and Hz equals K. The third equation can be solved for Z. Then we back substitute to find Y in the second equation, and then back substitute to find X in the first equation. In our example of solve the system, equation A is 6x plus 2y minus z equals negative 6. Equation B is 3y minus 4z equals negative 2. And equation C is 2z equals 4. This system is already in upper triangular form. So my first step is to solve equation C for z, and z pretty clearly equals 2. So I'm going to substitute z equals 2 into equation B. 3y minus 4 times 2, so that's 8, equals negative 2. So that means I have 3y equals 6, y equals 2. So the next step is to substitute y equals 2 and z equals 2 into A. So that's 6x plus 4 minus 2. So that's going to be 6x equals negative 8. X is negative 4/3. So the solution to this system is negative 4/3 to 2. So I can check that when x is minus 4/3, y is 2, and z is 2. Let's check c first. 2z, or 2 times 2, equals 4. So it checks in equation C. Let's check B next. So we have 3 times y, so that's 6, minus 4 times 2, so that's 8. That equals negative 2. So that checks. And now let's check A. So we have 6 times negative 4/3 plus 2 times 2 minus 2, and that equals negative 6. So that checks by using the calculator. 3 equations in 3 variables is 3 planes that intersect at a single point. In this case, the point is negative 4/3, 2, and 2. In figure 2 here on this graphic from the OpenStax open source textbook on college algebra, you can see part A. We have 3 planes that intersect in a single point. In part B, we have planes that intersect in a line, which shows a system with infinite solutions. In figure 3, we see all 3 figures represent 3 by 3 systems, but there are no solutions. 3 planes might intersect with one another, but not at a common point, or we could have 3 parallel planes and there's no solution. Well, what if we don't have a system conveniently arranged in upper triangular form? How do we go about solving that? Well, this is the process called Gaussian elimination. We pick any pair of equations and eliminate one variable, then pick another pair and solve for the same variable until you have upper triangular form, then back substitute, then check. Solve the system. Equation A, x minus 2y plus 3z equals 9. Equation B, negative x plus 3y minus z equals negative 6. Equation C, 2x minus 5y plus 5z equals 17. This problem is taken from the OpenStax college algebra textbook. There's always multiple ways to make this decision, but we're going to eliminate x first since the equation A has a positive x and equation B has a negative x. So we're going to keep equation A as it is, and we're going to create a new equation B. It will be equivalent, and it will be the same as if we added 9 to both sides of B, which will produce an equivalent equation. But 9 to the left of the equal sign is x minus 2y plus 3z, and 9 to the right of the equal sign is just 9. So we're going to add A and B together. So we will get y plus 2z equals 3. Next, we'll need to create an equivalent version of C. We need to eliminate 2x. So multiply a by -2 and then add it to c. It's just like adding -18 to both sides of c. That will give me a new equivalent c with the x eliminated. That's -y minus c equals -1. So we've almost changed the original 3x3 system into triangular form. There's one more step. We'll add b and c together. That's like adding 3 to both sides of c, and we will get an equivalent equation. So that gives me z equals 2. And there we can see the triangular form. So next I need to substitute back. So I'll substitute z equals 2 into equation b. So y plus 4 equals 3. That implies, or that means, y equals -1. And then I'll substitute y equals -1 and z equals 2 into a, and I see that x equals 1. So the solution to my system is x is 1, y is -1, z is 2, and this is the single point where the three planes will intersect. So we can check this by plugging x is 1, y is -1, and z is 2 into equation a, b, and c, and we see that we have got the correct solution. And we can also see this is the point of intersection of our three planes, the point 1, -1, 2. This problem is also taken from the OpenStax College Algebra textbook. Our first equation, x minus 3y plus z equals 4. Our second equation, minus x plus 2y minus 5z equals 3. And our third equation, 5x minus 13y plus 13z equals 8. So I'm going to choose to eliminate x from equation B. I'm going to add a and b together, which is like adding 4 to both sides of b, so it doesn't change it. Just remember that 4 in this system also equals x minus 3y plus c. So x minus x is 0. Negative 3y plus 2y is negative y, plus c minus 5z is minus 4z. 4 plus 3 equals 7. To get triangular form, I need to eliminate the y term from c. So I think if I say 2 times the b equation, I'll get negative 2y minus 8z equals 14. I'm effectively going to add 14 to both sides of c. So negative 2y plus 2y is 0, and negative 8z plus 8z is 0, and then I have 14 minus 12, so that's c. So I do have triangular form, but I have a false statement. This is an inconsistent system. There's no solution. So we can see if we look at this graphically, there's no single point of intersection, and there's no single line of intersection. There's no solution. In this example, we're going to solve the system. Equation A is 2x plus y minus 3z equals 0. Equation B is 4x plus 2y minus 6z equals 0. And equation C is x minus y plus c equals 0. So I'm going to simplify B. I'm going to multiply A by -2 and then add it to B. And I'll have -2A. So when I add those two together, I get 0 equals 0. Now this is a true statement. This is a system that has infinitely many solutions in the intersection that is a line. So it's a consistent system with infinitely many solutions. So for C, I'm now going to add A and C together and eliminate Y. So this will give me 3x plus 0y minus 2z equals 0. And typically what we do in these systems, we need to write still the xyz point, and we write those solutions where there's infinitely many solutions and the intersection is a line in the consistent system. We typically write those in terms of x. So I'm going to solve part C in terms of x. So that's going to give me z equals 3/2 x. And now I'm going to use my original part C. Remember, my original part C said x minus y plus z equals 0. And that means y equals x plus z. So y equals 1 plus 3 halves, so that's 5 halves x. So the point in question is x, the independent variable, y equals 5 halves x, and z equals 3 halves x. And this is a line. This system is dependent, consistent, because it has solutions. In fact, it has infinitely many solutions. So here's the graph of equation A. When we add equation B, you can see they're the same plane. Here's equation C. And you can see the intersecting is a line, infinitely many solutions.